Hello again. This is a continuation of the Dynamics Study Guide. I'm going to call it Part 2. Okay, we talked about inertia. And basically, inertia is mass. The tendency of an object to resist a change in its motion or a state of rest. If you have a lot of mass, you have a lot of inertia. And you're going to be difficult to change your speed if you're moving, or to get you into motion if you're at rest. That's the first law of motion. It takes a net force to move you from your state of motion, to change your state of motion or your state of rest. Now, weight is related to mass or inertia, but it depends on your location. For example, if you're on the moon, you have the same mass as you have on Earth, but you weigh less. So weight is gravitational force. Not little g, is gravitational force. And we signify it by a symbol W, or force of gravity, big F, subscript G. Talk about normal force later. Let's focus on the relationship between weight and mass. Okay, mass is a property of an object. Depends on how much matter is in the object, how massive the atoms are, and how many atoms you have. Mass doesn't depend on what planet you're near or on. Does not depend on. Mass is constant throughout the universe. So weight is gravitational force. Okay. Here's the equation for weight. Those little arrows signify vectors. Force is a vector, and acceleration due to gravity is a vector. Please don't call little g gravity. It isn't. It's the little g is the acceleration due to gravity. So basically, here's the equation, and it's just like Newton's second law is a variation of Newton's second law of motion. Weight equals mass times the acceleration due to gravity at your location. So we don't put a negative. Well, we can. We can put a negative on the acceleration due to gravity. But if you do, that's just representing the weight as downward. The direction of the acceleration, g, little g, is the direction of the weight, which is always downwards. Again, force of gravity is a vector. Its direction is downward. The acceleration that causes that gravity is downward, because the net force and the acceleration are always that it causes are always in the same direction. Okay, so that's a really easy equation to use. This is do some practice. Determine the weight of a 6 kilogram object on Earth or near Earth. So, what's the gravity is weight, or Fg if you want. Mass is kilograms. The unit for mass is kilograms. So weight equals mg, or fg equals mg. So that equals the mass times 10, 9.8 comes out to 60. The units will be newtons. They get 59 because they're using 9.8. We use 10. Okay, these are easy. So if an object weighs 245 newtons, what's its mass? W equals mg. M equals, I like to do the symbols. I like to do algebra with the symbols. Okay, so before I put numbers in, so W, I want to isolate M, I divide both sides by G. So this equals 245 divided by 10, which is 24.5. If you use 9.8, you'll get the mass to be 25 kilograms. Okay, the acceleration due to gravity, you know what that symbol means. That's little g is lower on the moon than on Earth. What's the following true about the mass and weight? Mass and weight of an astronaut on the moon compared to the astronaut on the Earth. Well, the mass is the same, like I said. So it's either that one or the others. So because weight equals mg, and m is the same, if you have a smaller g, you're going to have a smaller weight. So the weight is directly proportional to the mass and the acceleration due to gravity, but the mass isn't changing. So on the moon, the g of the moon is less than the g of the Earth. So the weight has to be less of the astronaut on the moon. Okay, so there we go. Let's let it be. Okay, so some people confuse this equation. They think that you have to be accelerating to have a weight. No, that's just the acceleration due to gravity. You have it if you're at rest, even. So this g, little g, is acceleration due to gravity, but you don't have to be freely falling or moving to have it. To have weight. You always have little g if you're near Earth, or on Earth, but that's why you always have weight, even if you're at rest. So this vase on the table has a weight downwards, even if it's not accelerating. Okay, now, is that the net force? Is the weight the net force? In other words, is it the unbalanced force acting on the base? Well, if it was, it would be accelerating according to F net equals ma, Newton's second law. But it's at rest, so there has to be another force that's acting on it that cancels out the weight so that the net force, is zero, or else it would be moving. So that's my question. What is that other force? So net force is zero. How do I know? Because it's at rest. Now it could be moving at constant speed and have a net force of zero. But this is just at rest. So remember, if net force equals zero, there's no external force, net unbalanced external force acting on an object. It's either at rest or moving with constant speed. In this case, is at rest. So what is that? What is that upward force? Okay, we call that the normal force. When something's pushing against the surface, in this case the vase is pushing against the table. The table pushes back to keep it from falling through the table. And we call that resisting force, the normal force. By definition, normal force, sometimes I just I call it normal force, capital N in a box, because it's easier to write in FN. Okay, so the normal force is always perpendicular to the surface that the object pushing against. Why is the vase pushing against the table? Because gravity is pushing it downwards. And then the table resists that push. Okay, so normal means perpendicular. That's a math term. Okay, so we got that. If the normal force pushing up equal and opposite to the weight pushing down. And that means the vase is in equilibrium, which means either it's at rest or moving with constant velocity. In this case, it's at rest. Okay, 14 Newton brick is sitting on a table. Okay, so the weight equals 14 newtons. So when they say something Newton object, that's just a weight. What is the normal force supplied by a table? Well, if it's not moving, it's at rest. The normal force has to equal the weight, which is 14 newtons. And it's upward, perpendicularly upward. Okay, these are all the same, but in this case they're being tricky. What is the weight of a 2 kilogram box? Okay, don't confuse weight and mass. So 2 times 10. 2 times 10 is 20 newtons. So it's a normal force if it's sitting on it at rest. Normal force would equal the weight, which equals 20 newtons. Okay, they say 19.6 because they're using 9.8 instead of 10 for G. Okay, so this brings us to the last law of motion, Newton's law of motion, called the third law of motion. So, Newton's third law. When object A exerts a force on object B exerts an equal force, but in the opposite direction on object A. Okay, this is really not too intuitive a law. For example, what if you're driving your car and here's a dragonfly, and you hit the dragonfly here. You hit that dragonfly. I don't know what dragonfly. Okay. And he smashes all over your car grill. So here's your car moving, and here's the guts of the dragonfly. Okay, if I were to ask you, Who applies the bigger force? The car on the dragonfly? Okay. The force of the car on the dragonfly. Let me do that. Force of the car on the dragonfly. Or the force of the dragonfly on the car. Force of the dragonfly on the car. Who would apply the bigger force on the other? Now, most people would say, well, duh. The car smashes the dragonfly, so obviously the car supplied a greater force on the dragonfly than the dragonfly did on the car. The dragonfly did not even make a dent in the grill. Okay, but that's a misconception. According to Newton's second law, Newton's third law, if an object touches another object, that second object applies the same force, but in the opposite direction. So we gotta say that the dragonfly on the car is equal to the force of the car acting on the dragonfly. It's just that the dragonfly's body can't take that force and it falls apart, whereas the car's body can. Okay? The result of a force, of a contact force, has nothing to do with its size. So if you threw if you hit a baseball and it went through a window, of a building, the baseball applies the same force on the window pane as the window pane does on the baseball, even though the window pane got shattered. Here's another way to express Newton's third law. For every action force, there is an equal and opposite reaction force. So, example, if a baseball went through a window, the force of the baseball on the window is the action force, and the force of the window on the baseball is the reaction force. Okay, so, yeah, it's important. You have to have two different objects to apply the third law. So a guy doing push-ups, you got the floor, and you got the force of his hands in contact with the floor. These forces are opposite but equal. Now, are they the same throughout? Let's not worry about that. Okay, here's a very useful Newton's third law. If you are in a canoe or a kayak paddling, the force of the paddle against the water equals the force of the water against the paddle. This propels the boat. You're basically pushing the water, and you're connected to the boat, and the water pushes back, and you and the boat are propelled forward. Same thing with walking. When this girl's walking, she applies a force. I did that in pink right here. She applies a force against her foot right here, is pushing against the floor. But the floor in green is pushing back in the opposite direction. And we push off the floor in order to propel ourselves forward. This floor pushes back with the same force. Now, why do we move and not the floor? Because we're less massive. We're much less massive than the floor and the earth, because F equals ma. Our mass is smaller. Our acceleration will be bigger than the Earth's acceleration backwards. Now, if we put that to a rocket in a rocket engine or a jet engine, well, rocket engine fuel, or firecracker, the chemical energy of the ignited gas molecules, it pushes the gas exhaust out. So that's the force of the exhaust. But as it pushes the gas molecules outward, it also pushes the rocket upwards. And so the rocket gets thrust. You might say, why is the rocket accelerating? How can it accelerate if these two forces right here? If these two forces equal right here, how can the rocket accelerate upwards? Well, the force of the exhaust is not acting on the rocket. So you can't say Fr, because Fr equals Fe, the rocket's not going to go anywhere. Okay, the force on the exhaust is not acting on the rocket. Only the force of the gas particles pushing against the rocket is acting on the rocket. So that's why we can accelerate. You don't include reaction forces when you're drawing three-body diagrams. So here's the rocket. There's the weight of the rocket right there. There is the force of the fuel, the force of the rocket because of the gas molecules pushing against it. So because Fr is going to be bigger than the weight, the rocket accelerates upward. So we could say the net force on the rocket because of the push against the rocket by the gas molecules, because the push on the rocket because the gas molecules exiting is equal to, the net force on the rocket is equal to the reaction force, because the gas molecules minus the weight of the rocket. Therefore, it can't accelerate it. Therefore, it equals the acceleration of the rocket. I mean, it's proportional with the acceleration of the rocket. Okay. Okay, this is kind of a trick question. If you're sitting on the Earth, okay, your weight obviously is produced by the Earth's gravity. What is the reaction force? Now, it's very tempting from what we just talked about, say the reaction force is a normal force. F subscript N, for capital N in the box. But that's false. Okay. So, think about it. The Earth is pulling on me. The reaction force is, just flip the object and the subject. The Earth is pulling on me. So the reaction force is I'm pulling on the Earth. Okay? So Newton's third law says that object A pushes on B or pulls on B object B pulls or pushes on A with the same exact force in the opposite direction. So it's not the normal force, that's the reaction force. It is, the Earth is pulling on me, I'm pulling on the Earth. That's what gravity's about. So this is letter D. This letter D. Okay, so what's the N then? Normal force. Well, that's the, I'm pushing against the Earth. The Earth pushes up against me with, if that is the normal force, but the normal force doesn't have to be there. I could be falling towards Earth, and the Earth will be falling upwards, rising towards me. If that force wasn't there, or that Earth wasn't there. I mean, if I'm off the Earth. Okay, so that's, don't push this one. That's the normal force. And more directly, the reaction force is the Earth, is me pulling up on the Earth. So you might say, why isn't the Earth rising to me if I'm pulling up? Let's say I jump off a platform and I fall towards the Earth, like a diver. Why doesn't the water in the swimming pool and the Earth move up to me? We both have the same force pulling us. Well, because of Newton's second law, F equals ma. This is Newton's second law. The mass of me is so much tinier than the mass of the swimming pool water and the Earth that there's no way that the acceleration of the water and Earth would be anywhere near the acceleration of me. My net force, because of that gravitational force, is going to give me a big acceleration, but it's not going to give the Earth, which has a huge mass, for the same net force. It's not going to give the Earth any acceleration that I can measure, even though it slightly does. Okay, here we go. This is, again, checking if you're still in the misconception land. Okay, if something smashes and a lot more damage, it doesn't matter who gets the damage more. Force is the same on both. My dragonfly, my car collision into the dragonfly is an extreme example of this. So this, according to Newton's second law, is what we choose. The force of the truck on the car is equal to the force of the car on the truck, but it doesn't matter who gets damaged more or it affects the result of the force. As you were saying, if you have a chair pushing, the reaction force, again, is the Earth pulling up at me. The action force is the Earth pulling on me. The action force is the Earth pulling on me, my weight. But the reaction force is really me pulling on the Earth. So, you pushing down, the chair pushing down on the ground, no. Gravity pulling down on you, no, that's the action force. You pushing down the chair. No, the chair isn't the issue. Ground pushing up on the chair. No. The best answer would be the action force. Okay, the action force is Earth pulling on me. The action force is me pulling up on the Earth. So the best answer would be you pulling up on the Earth. Now, because I'm pulling up on the Earth, the chair gets in the way. The chair pushes up on me. So none of these choices are really good. Okay, so this would be the choice. Choice F. Action force is the Earth's gravity on me, and the action force is me pulling up on the Earth. Okay, so positive physics, Unit 5, has this really nice chart showing all the different kinds of forces you'll encounter, at least in this class. Okay, so we talked about weight. Now, really the symbol for weight, if you're in AP Physics, symbol for weight would be F subscript be F subscript G. And I do lowercase w. Capital W isn't a good thing, letter to use, because capital W is work, another unit coming up. Okay, so weight is the gravitational pull of the planet, wherever you're near, on you. It's always towards Earth. So in these cases, whether you're moving, whether you're at rest, the weight is directly down. Now if you're on an inclined surface, the weight is not like this, perpendicular to the surface. No, it's straight down. Okay, if it's a ball, I don't care whether it's where it's moving, how it's moving. If it's really moving, or even if it's not really moving, the weight is straight down towards the Earth. Okay? That's important. Never draw weight as a slant. Don't draw like that. All masses are forces on each other, but it's only centered real large. Okay, so you're applying a force, a weight on anything, on the person next to you, but it's so minimal because your mass is so small compared to the Earth. So you have to be a huge object with a lot of mass to exert gravitational force. That's significant, that can be measured. So we'll do that in another chapter. Okay, let's go. Normal force, we already talked about, is the contact force. Whatever you're pushing up against, it doesn't have to be the ground. It doesn't have to be the ground. Okay, so it's always perpendicular to the surface. So here's a ball hitting a wall, in this case. The normal force is not the weight of the ball is like that. But the normal force isn't like that, like you're used to probably. Okay, so it's perpendicular to the surface that's contacting it. So it's as drawn right there. If you're riding up or down an incline, the normal force, here's the weight, directly down. Normal force would be perpendicular to the surface. it's not going to equal the weight necessarily. In fact, it won't ever. Okay, but the point is, normal forces are perpendicular to the surfaces that are pushing against the object. Okay, so tension, we haven't talked about that, but tension is easy. It's always a pull. It's always pulling on an object. It's, cable, rope, string, muscle, fiber. Okay? And it's always along the string or the cord, always in the same. It's always drawn on the string or the cord, and it's always pointing away from the object. The green thing, in positive physics, the green thing is the object. The bright neon green thing is the object. Okay, then we have some other ones. Turn to the next page. This is all in positive physics. If you look at the lesson, before you do the problems, they give you it. Friction. Friction we're going to talk about a little more in the next unit. In the next task we'll go more details. But friction always opposes the motion. And we give the symbol for friction is big F subscript F. The symbol for normal force is big F subscript N if you're in positive physics. If you're in AP physics, and the symbol for tension is big F subscript T. I'll use capital T. The symbol for friction is little f, but if you're doing positive physics style, AP physics, it'd be capital F with a subscript F. Drag is, friction is always opposite of the motion. Okay, so the object's moving this way in the first picture here. The object's moving towards the right, but so friction has to be acting opposite of that. If this bike guy is moving towards the right, friction as he puts on brakes or air drag is to the left. Okay, if this box is sliding down a ramp downwards, the friction is always opposing that velocity. Okay, if you have friction-free surfaces, you won't have friction. Like if this box was the cart on a ramp, or nice little friction-free carts, you're not going to draw friction. If it has wheels, the cart has wheels, we can assume that there is no friction acting on it. Okay, so drag. Well, this is friction as well. Air resistance. Drag. Positive physics is going to use a big D for drag, but again, that is really friction. Air friction. Okay, again, everything I said about friction holds true too. Okay, this helicopter's not going that way. Okay, it's not doing that. It's going forward. It's going forward. So the drag is opposite. The rocket's going upward. Now, you don't draw the velocity vectors in your free body. You don't connect it. You don't connect the velocity vector to the object, making it look like a force. That's a big mistake. Okay, so velocity is upward, and friction has to oppose it. The guy's velocity is air resistance, of course, that's a breezy feel when you're running or riding a bike. It's opposing the velocity. But again, these guys, you do not connect to the object. They're not forces. Okay. Now, they call any force that's propelling an object, they call that thrust or the applied force. And it's kind of weird. That's their way of showing it. TH or thrust or applied force. So I don't know. We'll keep their. I call it the force of push. Okay, but let's use theirs because you'll be doing positive physics. Their way of looking at it. Okay, so it could be a motor, supplied by a motor. It could be supplied by your legs as you pedal. It could be you pushing it directly, like this guy. It could be the lift. Well, we can just look at this and say it's the motor causing the rotors on the helicopter to spin, and the rotors are pushing against the air, and we call that thrust. Or a bird flapping his wings, that's thrust. Okay, so that's what you're going to be doing. That's what you'll be doing. I'm going to stop this video right now. You'll be using those kind of different forces when you do positive physics. So you should be able to unify positive physics right now. You should be able to complete that whole unit with no problems. Now, positive physics has, this unit has emphasis based on free body diagrams, FBDs. And that's just drawing all the forces acting on an object. Okay, so I make the object just the dot when I'm doing an FBD. Then I draw arrows pointing away from the dot. Pointing away from the dot. Always away from the dot. They didn't write this. Showing the forces. I label those forces. Okay, so this would be, for example, a person riding his bike on level ground. So here's the bike, here's the weight of the person. I'll use my symbols. Here's the applied force from him pedaling. I'll call that force of push or applied force. Okay, if I'm doing positive physics way, there's a normal force. It's going to equal the force of weight, and that's it's in the elevator, accelerating up or down, but we'll talk about that later. And there's probably air drag. And so I'll just call that friction. If I was positive physics, I'd call applied force A, and call the friction D for drag. Okay, notice all the arrows point away from the bike. They're all connected to the bike, and they're pointing away from the bike. The point. Okay, draw the arrows about relative to their magnitudes or their sizes. Okay, you can even show acceleration or the velocity, the direction of the acceleration or the velocity, but don't, that's not necessary, but don't connect it to the point right there. Don't connect it to that point. Only forces get connected to the point. Okay, these are easy. A cat sitting on a chair. Okay, so there's the cat. He has a weight pointing down and equal normal force pointing up. Sled pulling across an icy pond. Okay, so here's the sled. Let's make it easy by just making the force horizontal, but was slanted. Okay, but we won't do those yet. So there's my force of push, or my applied force. And here's the weight, of course. And here's normal force, should be equal. Okay? I draw the XY axis just I don't know, so I have a reference. Okay, you're not going to draw friction because on ice there might be a little bit of friction, but usually if it's on ice, there's hardly any friction. Okay, this is where I'm going to end. This is where we're going to end the first test. Okay, so important to see positive physics goes to much more practice and thought building than these two simple examples did. So I'll leave that for you to do. Next video, I'm going to show you, we're going to, I'll leave it at that. Okay guys, take care.